complex numbers, what we're talking about is normally we operate in the real number system, okay? And that's part of what complex numbers are. So if you remember, this was from that review chapter, our set of real numbers. We've got real numbers, natural, whole, integer, rational, and irrational. When you add to that imaginary numbers, we have now come up with the complex number system. So there's a real number, okay? There are imaginary numbers. Together, those sets of numbers are the complex number system. Yeah, if you want to take a picture of that, feel free. Okay. They don't overlap, but they can be combined together to create that complex number. Every real number is a complex number. Every imaginary number is a complex number. Okay. Notice that they are all contained in the big black box. So the black box indicates complex numbers. We've got our set of real numbers over here and imaginary numbers over there. The foundation or the basis for imaginary numbers is the imaginary number, okay? And I is the imaginary number. This particular program that I use doesn't allow me to really do italics very well, so that's why I wrote the I off to the side. Because typically the way you will see I is written like this. But throughout the rest of these notes, this will not appear as an italicized I. And what I is the square root of negative 1. Okay? And as you know, when you take the square root, you can't take the square root of a negative number because there's no number that you can square to get a negative number. It will always be positive. So what the inventors of mathematics did a long time ago was they said, bless you. What they said was we can still use these numbers in similar ways if we can make an accommodation for this square root of negative 1. Okay. Here's the thing that you need to know. All complex numbers can be written in the form a plus bi. And generally speaking, when we're dealing with complex numbers, you should put them in a plus bi form. And that's sort of just understood. Okay, so if you're not sure which form to put the number in, revert back to this. Now, what's important to understand about a and the bi part is that you have a real part, which is the a that doesn't have the I on it, and the bi you have the imaginary parts. Because every complex number can be written with a real part and an imaginary part. Now, when we think of real numbers, there is no imaginary part, right? It's just like 0i, but we don't write the 0i, right? When we think of just an imaginary number without a real part, we don't usually write 0 plus 7i or whatever. We usually leave that 0 off. But if they're very specific about saying it needs to be in complex number form, then you're going to want to make sure there's a real part and an imaginary part. And if that means putting zeros in somewhere, that's what you're going to want to do. So that's kind of the beginning part. Let's kind of get into it. So here's an example of what I was talking about before. Like, we can't find the square root of negative 16. You can't take a number and square it to get a negative. So instead of just abandoning the whole situation, what we're able to do is split it up. Okay? And essentially I'm going to take the negative out. Because I can find the square root of 16. And the accommodation that I was talking about before is, all right, fine. The square root of 16 is 4. Well, the change that we make is then if we always have the square root of negative 1, then we can just list that as 4i. So 4i, which is 4i. Okay. So we can still simplify it a little bit because now we have imaginary numbers that we can work with. We don't just have to stop, okay? And then we can use that in other ways that I'm going to show you here in a second too, okay? Are there any questions about that? Now sometimes the numbers aren't as nice, but I can use my properties with radicals the same way. So for example, if I had another problem like this, the square root of negative 27. Now, the way I like to describe it, and maybe you remember me talking about this, if we just take that sort of negative and pull the I out, that's the way I like to think about it. We pull the I out, and then I can deal with what's left. Okay, you if you haven't heard me say that before, you will hear me say it again. But starting off, what we want to really do is break it down as much as we can, like we did this first one. In doing problems like this, we want to find the biggest perfect square that goes into 27. What is that?
9.
9 is the biggest perfect square that goes into 27. So we want to think about this problem kind of threefold. The square root of 9 times the square root of 3 times the square root of negative 1. And that's that whole pulling the I out because this is just I. What is the square root of 9? 3. Now, one of the things that's interesting is when we simplify this, what we do is we actually start treating I like it's a variable. And we typically don't put it behind the radical. And the reason why is when you start writing and sometimes you kind of get in a hurry, sometimes it's unclear as to is the I underneath the radical or not. Because how far does this extend? How close did I put the I to the 3? So to avoid any confusion, what we actually do is just take the I and put it in front. So there's no chance it can go underneath, which is why I see an answer like this. Now, that being said, 3I root 3 is not A plus BI form. So if you are asked to put it in A plus BI form, in complex number form, you would have to, and notice how I overcompensated for the amount of space that I put in between the radical and the I. So I'm leaving no question about the fact that the I is not underneath the radical. And so if it asks for complex number form, I have to have a real part, which in this case is 0, and then the b, which is the number in front of I would then put together. So it just kind of depends on what form you're asked to put it in. Typically speaking, this is going to be preferred because of this idea that there's no I slipping under the radical by mistake. Okay? And then we're done. Are there questions about any of that? All right, let's keep moving. Okay? Let's talk about, this is the one thing that seemed like when I've taught this in the past gets confusing. There's going to be a recurring pattern that we need to follow. I squared, I cubed, I to the 4th. And we're going to talk about what all of that is. If I equals the square root of negative 1, if I square something that is the square root, what happens? Goes away. They cancel out. So if I square something that is square rooted, they are inverses of each other, and they cancel out. So I squared equals negative 1. And to me, this is where the power of imaginary numbers comes in. And I say this every time I teach it, because it kind of just blows my mind. And I'm being serious about this, right? Something that is imaginary. It's literally the figment of someone's imagination. It does not exist. Yet when I square it, it turns into something real. Okay? To me, that's where the power of imaginary numbers is. Because people say, well, what if it's imaginary? Why do we, can somebody make it up? Why do we do it? I hear that every year I teach, right? And you probably have said it at some point, or at least thought it. And that's why. The fact is, I can take an imaginary number and square it and get a real number. To me, that's mind-blowing. Maybe that's just me. All right, let's I to the 3rd. Okay, I to the 3rd, if we wanted to break that down, is actually I squared times I. I squared is negative 1. So I to the 3rd is actually negative I. Okay? I to the 3rd is negative I. And then I to the 4th is I squared times I squared, which is negative 1 times negative 1, which equals 1. This pattern, I to the 1st, I squared, I to the 3rd, I to the 4th, you should memorize. You should get that pattern down. You should not have to reproduce all this work. Memorize the pattern. It'll make your life easier. Because one of the things that you're going to be asked to do is evaluate I to random powers. And instead of going through all the hassle of figuring that out, I'm going to show you a little bit of a trick to do that. The key thing here is that everything is in this group of 4. And so that's where that's going to come into play. Are there any questions before we look at some of those problems? Okay. Some of you may remember doing problems like this before. I to the 6th, I to the 35th, I to the 81st, and feeling confused about it. Okay, I'm gonna hope to clean that up today. The goal here is to figure out how many I to the fourths go into those things. And the reason why I to the fourth is important is because it just equals 1. So if I can separate these into I to the fourths, I can find out what's left over, and that's actually my answer. So in this case, I to the sixth is I to the fourth times I to the second. Right? Yeah. Since I to the fourth is just 1, it's really I to the second. Which, what is I to the second? -1. So I to the sixth is equivalent to I to the second. Okay? Now, look at what I wrote above. That's where this gets a lot easier to realize. Okay? 6, which is the power from the original problem, I divide that by 4. That's telling me how many i's to the fourth go in. It's the remainder power that you use to determine what this will actually end up equaling. Now, what I'm going to show you for the next two problems, I'm not going to write it out like this anymore. I want you to focus on this division piece, okay? And it's always 4. You always divide by 4 because over here they come in groups of 4. Okay, and I to the fourth is 1. So if you can maintain that idea of whatever that crazy power is that I is raised to and divide it by 4 and find the remainder, that remainder is the key to figuring out what it's equivalent to. Okay? So for this next problem, all you need to do is take 35 divided by 4. And I don't even care about how many times it goes in evenly. It doesn't really matter. What's important is the remainder. Because what this is telling me is there's 8 i's to the fourth that go in, which is 1 to the eighth, which is still always just 1. So that's why this number in front doesn't really matter. It's this number that matters. Because in reality, what this means is that this is equivalent to I to the third. And that's why the remainders line up. Well, what is I to the third? Negative I. So I to the 35th is equal to negative I. Do the last one yourself. All right, what's 81 divided by 4? 20, remainder 1. Okay, 20 remainder 1, which means it's I to the first, which is what? It's just I. So one of the things that we don't do is write the square root of -1. We actually list it as I. Since this is the power on I. Okay. Now, if you're still not convinced that makes sense to you, the reason where that other part comes from is right here. So for this would be I to the fourth, right? I to the fourth to the eighth. So this 8 corresponds to I to the fourth is raised to. So this is really I to the 32nd, right? But this is 1 to the 8th. So 32nd, 32 and 3 gives me the 35. This would be I to the fourth to the 20th, which is I to the 80th, with 1 left over. But what I'm telling you is we don't need to worry about that part. But if you're wanting to understand why that division works the way it does, it's because of this. Okay? The key is the remainder. The remainder tells you whether you're going to get an answer of I, -1, negative I, or 1. All right, let's keep moving. Let's talk about operations with complex numbers. And again, to me, this is where the power comes in. Take an imaginary thing, combine it together with another imaginary thing, and somehow get a real thing. That can happen. Okay? We treat I like it's a variable, and we do everything with I when it comes to operations with imaginary numbers like it is a variable, with the understanding that it isn't a variable. Okay? But we can treat it that way. And that's what this says. Treat I like it's a variable and simplify the same way you would as if you had like terms. And the like terms are the imaginary part. You can combine the real parts together, you can combine the imaginary parts together. The one thing that I will say is you can't take a real number and somehow combine it with a real number and get anything but a real number. Okay? while you can take an imaginary and imaginary combined together, that often results in a real number. It doesn't work the other way. Here are the problems I want to work on right now. There are 3 problems up here. One is an addition problem, one is a subtraction problem, and one is a multiplication problem. Please work those out as if I was a variable. Go. So let's talk about the first one. There's the first step. So here's the first step for each problem. Okay? First off, since there's nothing being multiplied, I can basically just drop the parentheses here. Okay? For this second one, you have to distribute the minus. So it's minus 1 plus 7. And then this is straight up regular FOIL. Okay? Anytime you see an I squared, you should immediately change that to negative 1. Okay? So for over here, for A, I've got my real parts and my imaginary parts. Real parts here, imaginary parts. I've got some imaginary parts, and I want to change that to 1. So, notice what happened. Negative 2 plus 1 is negative 1. 5 minus 7 is negative 2i. That one's done. Complex number form, a plus bi. Okay. Negative 2 minus 1 is negative 3. 5 plus 7 is 12. That one's done. The only thing that I did in this one, I combined the like terms, and by changing this to a negative 1, essentially that makes that negative times a negative become a positive. So then my last move is to combine the minus 2 and the 35, which is 33, plus 19i. That way it's in complex number form. Raise your hand if you got all 3 correct. Very good. 2 out of 3. Less than 2. Okay, good job. Last thing that we need to look at, because we haven't talked about division at all. Oftentimes we will see division problems involving complex numbers. And what we're going to do is we multiply. So before we do that, before I get into that, let's understand what the issue is. One of the things that is not preferred in math is to have radicals in denominators. And if we remember that I is the square root of negative 1, I have a radical in a denominator. So our goal here when we simplify is to never have a radical left over in a denominator. And in this case, I have one to begin with. The way that we get rid of radicals in denominators, the phrase is called rationalizing the denominator. Okay? And in this case, I have a binomial in the denominator. So the way that we get rid of the radical in the denominator when I have a binomial is I multiply top and bottom by what's called the complex conjugate. Okay, it's conjugate, it's complex because this is a complex number. And simply stated, what the conjugate is the exact same numbers except the sign in the middle changes. Okay? And the reason why we do that, I'll explain here in a second. It guarantees us something. So in this case, it's going to be 3 minus 5i. And I can't just multiply the bottom by it. So the same numbers, except this changed from plus to minus, I have to do to the top as well. Okay? So before I explain why this works, I want you to go ahead and do that multiplication. So on top, you have distribution. On bottom, you have FOIL. Okay? And what should happen if you do it properly is there will not be any i's left over in the denominator. Okay? Which means there's no radicals in the denominator. So go ahead and do that, and then we'll come back together and talk about it a little more. I want you to understand first off why the conjugate works. Okay? Notice here what we've really created. Right? Think about when we were doing factoring earlier, and we had a difference of squares, right? That was square root, 1 plus 1 minus. That's what the conjugates are, right? What happens when I FOIL binomials that are the same except different signs is those middle 2 terms will cancel out. This is the F part of FOIL, and this is the L part. The O and I cancel each other out. So that's why conjugates work. And what will happen is, on the last term with a complex number, you'll always get an I squared, which will turn into a real number. And then the middle 2 terms that have just the I should cancel out. And that's true for not just complex conjugates, that is true for real conjugates as well. So if it said 3 plus square root of 5, 3 minus square root of 5, then those middle terms would cancel out and the square roots would go away that way as well. The reason that the conjugates work is because of what I've written up here, okay, with the O and the I sort of dropping out of factoring, okay? So when I multiply it out, on top I get negative 6i plus 10i squared. On the bottom I get 3 minus 15i plus 15i minus 25i squared. So again, this is an illustration of how these middle two terms cancel out. Okay. We change our I squareds to negative 1s, which changes my signs. Okay, so I got negative 6i minus 10, and these middle two terms cancel, and so instead of it being minus 25, it becomes plus 25. Okay, and then the last thing we do is combine the bottom. Now, generally speaking, we want to put them in complex number form. So there's a couple issues that we have here. So we want to put it into a plus bi form and reduce it. So what we do in order to do that is we split this top up by putting 34 on the bottom, and then the I term comes second. So when I split them up, this is where I'm at right now. Okay? This is the negative 10 over 34. That's the real part. And then the negative 6 over 34. And notice how I slid the I to the side. I did that instead of putting it up with the 6 because bi, it clearly demonstrates or displays that the negative 6 over 34 is the b, with the I kind of being separate. Now I just need to reduce. Okay? So what goes into 10 and 34? 2. Anything bigger than 2? Okay, how about 6 and 34? Anything bigger than 2? No, 2 in both of those. What I'm left with is negative 5 over 17, that would be A, minus 3/17, that would be BI. That would be my final answer. There's one other thing I want to show you real quick, in case this happens, and I don't recall if it does or not. But before I talk about that, do you have any questions on this? So the division part really ends up being a bunch of multiplication problems. The key here is understanding that you have to multiply by the complex conjugate. When you do that, then you're just doing a bunch of multiplication, simplifying, reducing. So here's the part I want to talk to you about. If I have a problem like this, okay, maybe typically speaking you looked at it and say there's no issue there. Well, the issue is I have a radical in the denominator, which is bad. But you say, maybe you say to yourself, well, what's the conjugate of 3i? There's supposed to be a binomial. I don't have a binomial. What am I supposed to multiply that by? Okay, so there's two ways to think about this. One, if you think about 3i as 0 plus 3i, what's the conjugate of that? 0 minus 3i, which in reality is what? Negative 3i. Okay, so if you run into a situation like that, that's all you really want to do. The conjugate is really just the same number with the opposite sign of whatever it is. And that will obviously get rid of that. Now, the other thing that you can do when you run into a situation like that, because let's just finish this. This is negative 6i, and that's going to be 9, okay, which is negative 2/3 I. Let's look at it a different way. If the problem is just the I, because in reality that's the problem. Okay, let me show you, look at it a little different way. I could actually just multiply the bottom by I to make it turn into I squared. Right? So that gives me 2I over negative 3. Same thing. So when you run into a situation like that, if you want to keep the idea of complex conjugates working for you, you want to use this. If you understand that the whole thing is try to make this an I squared, which would turn it into a real number, you can do it this way. I'm telling you, I don't care which way you do it. Either way, you're gonna eventually get the same answer, the correct answer. There's only one answer. Okay? But when you see just an I sitting down there by itself and you can't cancel it on the top with something, you can go about it either one of these two ways. Okay?